Aloha class. Today we're 6.2, integration by substitution. One of my favorite little topics here is use substitution. It's kind of a technique that you're going to use from here on out for the rest of your math lives as you go on and take higher level. It's a technique we use to make really difficult problems much more doable. And talking in terms of the AP exam, we're topic 6.9, integrating using substitution. We're going to call it U-sub. Okay, so we're going to integrate using U-sub. All right, here we go. A little bit of a background here to get us started. Warm up. Tell me what each one of these following guys mean. Okay, so what the heck does that mean? Hopefully we know that that means the integral from a to b of f of x dx. Remember, that is going to give me the exact area. Ooh, that didn't look very good. Under the curve, or from the curve to the x-axis, under the curve, from x equals a to x equals b. Okay, now what if I get rid of that a and b and I don't have limits? And that means we have no ends of integration. This means you cannot find the exact area, right? Cannot find the exact area. So it's important to always understand the difference between what we call a definite integral and that is called an indefinite integral, right? So definite integral is when it's defined, and indefinite integral is when we say it is not defined, okay, if you need a little bit of help of a reminder. Okay, indefinite integral, the set of all antiderivatives of a function is the indefinite integral of f with respect to x and is denoted by the following. Okay, note, an indefinite integral finds a family, okay, where you're going to get really into this when you look at the 6.1 video. Okay, but it's a family of functions, okay, a family of functions whose derivative is the integrand. Okay, that's how we kind of get the words derivative and antiderivative. Okay, corollary is fancy for, hey, if we have a theorem and we base something off of that theorem, or it's like a subsection, we call that a corollary. Functions with the same derivative, and there's going to be functions, believe it or not, that have the same derivative, differ by a constant, because what's the derivative of a constant, class, right? It's 0. So if f of x is equal to the derivative, okay, then the antiderivative of f of x would just be the antiderivative plus c, where c is the constant of integration. Now, you're probably saying, what the heck does all that stuff mean? You know what? It's going to make a lot of sense when we start doing a whole bunch of problems. So let's just get after this. You're going to hit pause right now. If you cannot answer these guys right now, you might be in a little bit of trouble. So see if you can hit pause and answer all of those guys. All right. You unpaused it. Hopefully you filled these guys in. Let's do it. X to the n. That's a power rule. So the antiderivative of that would be x to the n plus 1, but then I have to divide by a n plus 1, and since it's an indefinite integral, I have to add a plus c. 1 over x, the antiderivative of 1 over x is the natural log of the absolute value of x plus that constant. Okay, the derivative of e to the x, well, the antiderivative, of e to the x is e to the x plus c. B to the x, right? That's a little bit different. Well, that derivative would be b to the x times the natural log of b, so the antiderivative would be to the x over the natural log of b plus c. The antiderivative of 1 would be x plus c, and the antiderivative of sine, believe it or not, would be negative cosine x plus c. Remember, good practice is what are the derivatives of these? And if I do that, I should get those as all of my answers, correct? All right, let's keep going. The antiderivative of cosine would be sine x plus c. How do I know that's right? Because the derivative of sine is cosine. The antiderivative of secant squared, well, that's tangent. How do I know that? Because the derivative of tangent is secant squared. Ooh, this guy begins with a c, so it's probably got a negative in it. Right now, how did I know that? Because the derivative of that is that guy, right? The two negatives would cancel themselves out. Oh, that looks like an inverse trig. Which one is it? That's inverse sine, right? That's inverse sine of x plus c. Oh, that's an inverse trig. Which one's that? That's inverse tangent. Okay, and there's obviously so many more that you better know. but you better know all of those guys, okay? If you don't, you're really, really going to struggle with the rest of AP Calc. All right, today we learn a strategy to deal with more antiderivatives. First, a quick review of the chain rule. Let's see if we all remember the chain rule. Example 1, take the chain rule right now. Here we go. Let's go. F prime of x is equal to, drop that inside, outside. Do the outside first. Don't you dare touch the inside. So 12 minus 1 is 11. It's 11 in French. Times, I've got to chain it, 12x to the third, right? And then I can simplify 144, x to the third, 3x to the fourth minus 5 to the 11th. So guess what? We're going to have to go backwards. Whoa, how the heck do you go backwards, Holmes, if it's the chain rule? That looks way too tough, but that's why we got use of. Okay? Example 2, I just want to know whether you think each antiderivative would have a chain rule involved with it, okay? So make sure, I'm going to pause for like a millisecond, and then you see, just say yes or no, okay? The antiderivative of sine of 4x, is that an antiderivative where you're going to have to undo a chain rule? And hopefully you're like, for sure, Mr. T, because I have an inside and I have an outside. So yes, for sure, right? Okay, what about B? Is that going to have an inside and an outside where I would have to undo a chain rule? For sure. And why? Because that's an inside. Ooh, square roots. But then I have that too? But wait a second. Well, the derivative of that is 3x squared, and that's right there. So yeah, that definitely looks like it's got some type of a chain rule going on. What about this guy? This one kind of does. But that's my inside, and the derivative of that would be 3x squared, but I don't have an x squared anywhere. I just have an x. Oh, no, that one does not. Hopefully you understand the difference between those three examples and why A and B would be an example of undoing a chain rule, and B and C would not. And you could also distribute that to get x to the fourth minus 5x. Okay, that wouldn't be one either, right, class? And so there's a number of reasons why C is not. And A and B, hopefully you saw a little bit of why that actually would. So when the heck do we use U sub to help us to make a chain rule much more doable? You use when you see a composition of two functions. Okay, so that's definitely one we want to use U sub. Or when you see a function, this is like A and B, and its derivative, Okay, we're going to get into this as we do problems. It's going to make a lot more sense. It says let U be the inside function, and then we're going to do this stuff. Don't worry, we're going to do it. Be sure to list this. Don't worry, I got a technique, you guys. Easy peasy Japanese, all right? Then you find an antiderivative with the U, and then just make sure you resub, okay? So the best way to do this is let's get after it and why U sub works. Oh my gosh, that just looks so hard, it's crazy. But guess what? It definitely looks like I have an inside. And that's how you want to attack these guys. What do we think the inside is? That's what we're going to let our U equal. I'm going to let U equal x to the fourth plus 2. Okay? Now, all I have to do now is find the derivative. du dx, right? Because I'm going to find the derivative of U with respect to x is 4x cubed. And then here's a technique that is going to help anybody that's been struggling this year be really good at U sub. Okay, and that is we're going to solve for dx. Now, some textbooks won't teach this, but I have found out through the years that this really helps students to get really good at this. Okay, so there we go. And we're going to box my dx equals, and we're going to box what U equals, because I'm going to use substitution. Okay, now let's substitute. I'm going to put this U in for that right there, and I'm going to substitute my dx. Everything else you leave. Okay, so I'm going to substitute the two things that are circled there. And I'm going to leave everything else. X to the third, I'm not going to substitute for that. Square root is still there, but I'm going to put a U where that x to the fourth plus 2 was. And my dx, I'm going to plug in a 1 over 4x cubed du. Now, hopefully you're like, oh, snap, Mr. T. Those bad boys cancel out. Yes, they do. 1 over 4, that's a constant. I'm going to pull that bad boy out. That's a square root. I'm going to write it like U to the 1/2 du. Oh, I can do that, right? And that's exactly why we do U sub. That problem looked impossible from the get-go, but now it's really, really doable. So let's go ahead and do it. This is just a power rule, right, class? So we're going to add 1 to that guy. And if I add 1 to that guy, I get 1/2 plus 2 over 2. So I end up getting u to the 3/2, right, class? But then I have to divide by 3/2. Ooh, that's just yucky ducky, right? And then it's a plus a c in that, right, class? All right, let's keep on going. Now, that 3 over 2 I'm going to bring out in front. But we all know we would never want to divide by a fraction. So instead, I'm going to bring this all out. I'm going to multiply by the reciprocal instead. And then I get u to the 3/2 plus c. And then I'm going to do a little bit of simplification. Bada boom, and I get 1 over 6 u to the 3/2 plus c, because remember, a number times a constant is still just a constant, and then we just have to make sure we finish this bad boy out. And since my original problem had x's in it, guess what? We're going to resub that x. That u, I'm sorry, and u was x to the 4th. What was it? Plus 2 to the 3/2 plus c. Boom. Done. And you know what? If I really want to get super good at u sub and get every problem right on a test, if I have time, I'm going to check this guy. Let's find the derivative of this in blue. That's just a chain rule. Drop that 3/2. What do I get? 3 over, I get 3 over 12, which is 1/4. Don't you dare touch the inside, right? You subtract 1, I'm going to get 1/2, but then I got to chain it. 4x cubed. Now let's simplify that guy. Go away, boom. Let's rewrite it like that. Are you serious? That's the original problem. Oh, that means I did it right. Sweet. 100%, Mr. Tanaka. I don't care what you say. I got it right. Why? Because I checked it, Holmes. Right? So that guy's good to go right there. Let's keep going. I definitely need some spacer. Ooh, this guy looks kind of tough. But all I have to do when I have a very difficult problem that looks like the composition of 2 functions and say, hey, what do I think the inside is? And a lot of you guys are going to say it's 3x. Why? Because it's in parentheses. And that's a very good guess. But if I make my u 3x, my du is going to be 3 dx. And that means dx equals 1 over 3 du. And if I substitute that stuff in there, it gets me nowhere. So I got to try something else. And guess what? This is kind of a giveaway, right? Because I taught you guys when we did this earlier with our chain rule problems, that's the way we wrote it. And so if I looked at the inside, hey, guess what? My inside would be that. And then what's the derivative of that? Well, the derivative of that is cosine of 3x. Don't you dare touch that inside, but you got to chain it. Now, it really would be du over dx, but we're going to start saving some time. Okay, and then I'm going to solve for dx, just like I said in that problem before, and you get this. Okay, if you're not following, you better come in. You box your dx, you box your u. And watch how much it cleans up when I do that. I get the integral. Okay, I'm going to substitute that in for there, and I'm going to substitute my dx in for there. Everything else has to stay. So I end up getting u squared, right? And then I still have this cosine here, right? I'm not substituting anything in for that, but my dx is 1 over 3. Oh, but sweet. Oh, sweet. Those dudes cancel out. The 1/3 comes out. For real? Look how okay that is. Oh, I can handle that, Mr. Tanaka. That's just a power rule. You add 1, you divide by it, you add a c. I got 1/9. I'm going to bring that 9 out. Still u to the 3rd, but I'm not going to put u to the 3rd since my problem started with x's in it. It's got to end with x's in it. How do I get that? Well, I know what my u is, so I'm just going to put it back there. And then guess what? I could check my answers if I wanted to, but I got it right. All right, let's keep on going. Stuff's kind of fun, right? Kind of fun. Example 5. Whoa, this one, does this really look like it would be a chain rule or a composition of 2 functions? Well, there's a lot of things I could try. We're not going to go through the whole gamut. This is definitely a u sub. Now, why is it a u sub? Because I have a function, which is x squared plus 2. And guess what? What is the derivative? It's 2x. And the derivative is in the problem because that x matches up with that x. It's okay if that 2 doesn't match up. It's all about the variables, okay? And then if I solve here for dx, I'm going to get 1 over 2x du. And sometimes it will take a little bit of trial and error. And this is one section where you want to practice these problems like crazy because the more practice, the better you're going to get. Okay, so we have the integral. Okay, and let's go ahead and do my substitution. What am I going to substitute? My u, that's u's on the bottom. I'm going to, that x has to stay there. And then the dx becomes 1 over 2x. Oh, sweet, See you later, alligator. The 1/2 is a constant and comes out. It's 1 over u du. Oh, I know what the antiderivative of 1 over u is. The antiderivative of 1 over u is the natural log of the absolute value of u plus c. Oh, snap, I can't have a u in my final answer, so I go ahead and plug that u back in, which happens to be x squared plus 2 plus c. Done. Not bad, huh, class? Now, that's just the part 1 of this u sub. It kind of gets more and more crazy, which what does that mean, homie Holmes? That means more and more fun. Yes, it does. Keep watching these videos. Keep practicing. This is a prime example of working in your worksheets and trying some of these on your own will be huge. Keeping these videos to about 15 to 20. So aloha, and we will see you on part 2.